Okay. Welcome, ladies and gentlemen. Welcome to the Sustainability Hub. My name's Dr. Paul Lunt, and I'm an environmental scientist and academic here at the university. And my area of research is in nature-based solutions and also habitat restoration. And I'm going to be kind of leading off this session to talk about this wonderful material, biochar. So we're here really to celebrate this material. But before I do that, a few housekeeping things. First of all, can you make sure you've got all your phones switched to silent, please? Can I also, just in terms of the loos, for those of you not been to the Sustainability Hub before, we've got toilets in the back there. We are not expecting a fire alarm, but if we are, you've got a very good exit there out into the garden away from the building. So just bear that in mind. I think we can all make it out there. And then I would also say that we've got a whole list of exciting speakers here this afternoon. But if we could, please, can we leave questions to the end? So we're going to have a Q&A session in the end when all of the speakers will come down to the front and sit down here to take your questions. Okay, so I'm going to kick off then with just giving a little bit of an overview. So biochar, well, it's nothing new really. The indigenous communities in the Amazon have been using biochar, terra peta as it was called, black earth, for some 2,500 years for increasing their food production, soil fertility. And indeed, it's those layers that have been left behind in the Amazon that give us an idea of the recalcitrance, the kind of durability and longevity of that biochar material. So really, ancient solutions often hold the key to modern problems, and biochar is a compelling nature-based solution for several of our modern environmental challenges, as we're going to hear about today. So the information to be presented at the conference suggests that the benefits could even be greater than we originally assumed. So we're going to be focusing on the uses and applications of biochar, and we've got an exciting lineup up. So we've got speakers basically on 4 key themes. So we're going to be talking first of all about carbon capture, then moving on to soil health, and then on to water filtration, and finally looking at the insulation properties of biochar in building performance. And then we'll have the Q&A session at the end of this. So in terms of the actual feedstocks then, on the definition for biochar, now I'm kind of talking to a pretty well an expert audience here, but biochar is basically the incomplete kind of pyrolysis of waste materials in particular, and lots of different feedstocks that are used, everything from sewage sludge, animal manure, woody material, which we're going to hear about in the first session, food waste and crop residuals. And this is heated up to a range of temperatures from 300 to 700 degrees. You can even go as high as 900 degrees in a flash pyrolysis. And the material is high carbon content, high cation exchange capacity, which we're going to hear about, high porosity and high stability. So benefits, well, there are many benefits, and we're going to kind of cover those in more detail, but certainly increased water retention and nutrient holding capacity is a really key one for our soils. Porous structure and large surface area, which is a key kind of attribute of them. Improved microbial activity and pH balance for many of our soils, particularly our more acidic soils, and high surface area and absorbing capacity. And in terms of the pollutants that it removes, heavy metals as well as organic pollutants and pathogens, as we're going to hear about. So I've just kind of compiled this table really, which is just a quick comparison of the carbon capture and storage methods. And in many ways, biochar is arguably the most readily scalable carbon sequestration option in terms of its reliability, low technical requirements and capital costs. I mean, just to have a look at some of the key things here, which I've highlighted, if I can get this to work. Sure, it's going to work. So you probably can't quite see that. But in terms of the first screen there, so I've compared basically biochar to woodlands in terms of carbon capture and storage, peatlands, which is a love of mine, and then more on the technical side, direct air capture and deep carbon storage. And in that first column there, you can see in terms of durability, as I mentioned earlier, we're looking at potentially centuries. So this material can be locked up in the ground or wherever it's going for centuries, as opposed to woodlands, which is decades, peatlands, millennia, and the more technical side also could be millennia. But there's lots of unknowns associated with those. In terms of the co-benefits that we're going to hear about a lot today, we've got our soil fertility and waste management, which is really key, water purification, and the fact that it's non-technical. Costs, well, you could be looking at kind of $100 to $300 per tonne of biochar for production. So the costs are actually a lot lower than those for direct air capture and deep ground carbon storage. And with waste material, we've got potentially a lot of scalability. So making use of the circular economy for our waste materials is really kind of key. And yeah, very stable material indeed. So we at the kind of net zero futures team and Tracy Ann in particular have been producing reports for many of the folks here, and this is just one of the ones that we produced for Cornwall County Council and Conserve, where we were looking in particular at the kind of barriers and process and opportunities, I suppose, for biochar. So we had a look at the kind of biomass source and looked at the accreditation process, many accrediting organisations, but European Biochar Industry Consortium. Had a little think about our baseline, in particular baseline scenarios where we get the material from, thinking about the actual pyrolysis and thinking about the issuance and the fact that the actual credits aren't issued until much later in the process during the actual application stage. And applications, of course, construction materials, soils, etc. Life cycle assessment. So it is quite tricky in terms of looking at the kind of source materials. Have to do a full life cycle assessment of the carbon in order to get the verification. And in particular, interested in the original use of the material, the waste material, which is really key. If you have a material that is burnt, then you can obviously get the entire carbon credits for that. But if that material becomes part of a long-term store that is put into ground, then of course, what are you adding? What's your additionality? And additionality is the really key word with carbon capture and storage methodologies. So the verification certification is by no means simple, particularly when you think about comparing to the baseline scenario, and it's going to be different depending on what feed materials you're putting in and what the original use of those would be, and also challenges associated with emissions. So methane can be a particular emission in terms of the life cycle assessment, depending on your waste stock. You might be removing that from your equation and reducing the amount of carbon, therefore you're storing. Contamination concerns, depending on your feedstock as well, particularly if you're talking about waste material, sewage waste material. It might well be that you've already got heavy metals and things like that that you have to deal with. And then you've got the market dynamics, how much things are worth. Well, there's no doubt that the price of this is only going to go up, but it's a little bit uncertain, and I particularly realise that for those of you that are working on the application side of it. But yeah, a wonder material. So we're going to hear, first of all, talking about the feedstocks for our we're going to hear from Alistair, and Alistair is from the 1,000 Year Trust, Kabila, and they've been planting lots of trees, because I was out there just early in the year and seeing the hundreds of trees that have been planted as a feedstock. And then we're going to hear from Tom about the use of those feedstocks potentially produce biochar. So over text.
I think this thing's on. I don't know if I'm using the mic, but come over here, and then I guess this is the clicker thing. That's all right. Yeah, no worries. First of all, welcome everyone. I just want to say thanks to the University of Plymouth and the Net Zero Exchange for putting on this great event to talk about all things biochar. Like Paul said, I'm kind of focusing on the feedstock aspect of this and sort of what role I think biochar can play in sort of land management over the next 20 years from a sort of woodland creation and a woodland restoration and management perspective. So in theory, this should go, there it is. All right, so just a quick background about me. Yeah, like Paul said, I recently graduated from the Eden Project with a master's in land and ecological restoration. But over the past 3 years, I've been involved in a number of biochar projects, sort of hands-on experience, all the way from the sort of small-scale pilot projects and then also working on larger sort of operations. So the picture here was I spent 3 months in northern Thailand working with a network and a charity with over 100 landowners, and they were enabling farmers to produce biochar to help tackle the slash and burn issues that go on there, and in turn create a lot of health issues through smoke pollution. So that was a really good experience. And also I spent all last summer making biochar for a study that I did on soil water retention for my master's thesis, which I'll touch on towards the end. But today I'm here on behalf of the charity I now work for. We're called the 1,000 Year Trust, which I know a few of you might be aware of in the audience. But we're one of the only charities in the UK that is dedicated solely to the protection, restoration and expansion of temperate rainforest habitats. So we're based on an upland hill farm, a 300-acre upland hill farm, of which 100 acres is a 3,500-year-old ancient temperate rainforest. And over the past couple of years, we have been working to expand that vestige. And in doing so, we've planted over 40,000 native trees across 200 acres of degraded pasture. And this kind of presentation serves as a summary of conversations I've had with planting contractors, other site managers and developers on how biochar might bolster on to being an appropriate sort of strategy for managing the waste residue that comes out of woodland management. So why are we all here? Biochar. I know Paul gave a definition, so I'll breeze over that. But in terms of the sort of ecosystem of conversation around biochar, I like to think of it in three separate buckets. The first being feedstock, so what are we putting in, what are we making biochar from, the more technical side of things and the actual reactionary process known as pyrolysis, and then also what do we do with it when we've got it, what's the application and end use. And I'll give you a clue, it's not burning it. So moving on, so yeah, what am I talking about? Like I said, we've just planted 40,000 new native trees, and unlike managing woodlands for commercial forestry, with native woodlands, we're managing this for biodiversity, which means we have to do a certain level of thinning over the first 20 years of this woodland's life. So out of those 40,000 trees, we will actively thin 10 to 20% of this wood, creating a sort of waste forest residue. And at a small scale, this isn't too much of an issue because it can be left as dead wood, which is really good for site ecology. But as we sort of ramp up in our tree planting targets, this could then in turn sort of produce this excess of waste biomass, which I'm kind of proposing and sort of outlining the opportunity around what happens if we would divert that into biochar production. So just for a bit of context on the policy level, back in 2020, why are we going to see more trees in our landscape? Back in 2020, the UK government committed to increasing canopy cover from 13 to 17%. And on a county level, this means Cornwall has to plant 8,000 hectares of woodland per year between 2020 and 2030. And that will result in an average of around 13 million more trees in our landscape, all which will need managing and thinning within that first 20 years. So I'm not going to go too much into the details of the numbers on this, but I did some sort of modeling around different scenarios. So say if we take that lower boundary, that would give us 1.3 million young trees that would be produced in terms of waste biomass from our woodland management. And if that was all directed into the biochar production, Cornwall would be able to lock up approximately 220,000 tonnes of CO2 equivalent by leveraging off that sustainable source of feedstock. So this is where I think building a network of landowners and developers and academic bodies in Cornwall will be sort of integral to successful biochar projects, especially as we start to scale up with technology. So for my master's project, I worked in collaboration with a forestry plantation just outside of Liskeard, and I was speaking to a lot of land managers about their sort of issues around waste biomass, and the two key things that always came back were rhododendron and conifer brash. As we know, rhododendron is a non-native species, which is posing a significant threat to UK woodland ecology. And we spend millions of pounds every year removing and processing rhododendron, either by slash and burning or through using glyphosate in the stems. And one thing that's really good about rhododendron as a shrub is it creates really dense stems, which is appropriate for, well, which is great for the sort of pyrolizing process. And secondly, conifer brush. As our summers are getting sort of warmer, longer and hotter, there is sort of increasing risk around fire. So we were talking about how can we direct and collect conifer brush and turn that into biochar, mitigating that risk and also giving more access for people using the site recreationally. Lastly, for my dissertation, I took both of these feedstocks, made biochar out of them, and then amended soils with biochar at different application rates and different particle sizes. And I was looking at two key properties. I was looking at soil water retention, and I was looking at pH. And now these are just snapshots from my thesis project, so I'm not going to go too much into the detail, but basically what I found is if you crush biochar up really fine, that can significantly improve a soil's ability to retain water. But when you start getting to the higher particle sizes, 4 mil and 8 mil, you actually reduce the soil's ability to retain water. So if we're using it for that sort of context, it's important to understand what particle size practitioners should apply biochar at, especially when in soil. And then also looking at pH and seeing what impact that has on soil. And as you can see, which is kind of well established, biochar has a liming effect. It's slightly alkaline and can reverse acidity in soils, which is quite a nice circularity piece around the rhododendron, because rhododendron can alter soil chemistry and create acidic conditions. So maybe we can produce biochar out of them and then reapply that to the soils to help that land restore itself. So I don't think I did a thank you page. But Tom's next. But thank you for listening. And have a good rest of the trip.
Great. Awesome. Yes. Hello, everybody. Nice to be here. Two really great sort of introductions to biochar. So for context, Restored, we're a biochar, project developer. We make biochar here in Cornwall, and I'm going to be talking about the sort of, the carbon removal side of things, as well as, like the business case of biochar, and learning from our experiences over the last 18 months. So, just to quickly say, I came at biochar from a carbon removal angle initially. My background is in carbon removal. I did a podcast on it for about 4 years and then worked for a carbon removal marketplace. So basically sold biochar credits, direct air capture credits to some of the leading buyers of these offsets in the world. And what we always would say and have the conversation around with these buyers is that, yes, we need to reduce our emissions. That's the most important thing. But at the same time, we also need to be radically increasing the amount of carbon that we're removing from the atmosphere. And biochar is one of those methods. This is a nice way to frame carbon removal. Everyone probably seen this bathtub analogy before, but essentially what's happening to our planet is, or if we imagine the planet's a bathtub, we imagine our emissions or greenhouse gases are increasing. That is the water level rising in the bath. What we need to do is turn the taps off. That's emissions reduction. And then at the same time, we also need to pull the plug, because the CO2 has a half-life like many other greenhouse gases, and we need to actively remove those from the atmosphere. So I don't need to go into detail about biochar because Paul and Alistair have done a good job at describing it. I can focus actually on the products. So we've talked about the physical char itself, but we've also got a few additional products that come from producing biochar. So you've got the physical char, you've also got a carbon credit, which can be associated with that. And then you also produce waste thermal energy. So it's an exothermic reaction. And as a business, we're looking to see whether we can tap into all three of those products as opposed to just the physical char itself. So on the credit front, oh wow, my slide's gone really odd. I'll try and explain what that sort of gobbledygook is. As Paul mentioned, there's a bunch of different ways that you can reduce or remove CO2 from the atmosphere. Biochar sits quite neatly into this middle ground. So it's not a nature-based solution like a forest reforestation or afforestation, but it's not as high-tech as something like direct air capture or enhanced ocean alkalinity, for example. Biochar sort of sits in the middle here as a sort of engineered / nature-based approach. And when I'm talking about these prices, this is for a carbon credit. So, for example, a buyer is willing to spend 150 to 200 pounds per ton on a ton of biochar carbon removal. That's what we've done with some of our buyers. And to date, in terms of the carbon removal potential, 92% of all carbon removal credits that have been produced and delivered are biochar credits. So there may have been many more DAC credits sold, for example, but in terms of actual deliveries, biochar is leading the way. And that's really to say that it's a solution that's here today that just needs to be scaled. So there's a supply and demand gap. I'm talking again from the perspective of if you imagine you were a big company that wanted to buy carbon credits. What we're seeing in the market is that there's this sort of gap starting to emerge. So as companies get closer to their net zero target dates, could be a 2030 target, could be 2040 or beyond, what's happening is that their need for carbon removal is growing. And that's because there is no net zero without carbon removal. Otherwise, it would just be zero emissions. There's going to be something to net off, and that's when carbon removal comes in. So as we get closer to companies' net zero dates, we're going to be seeing, and that we are already seeing, an increased demand for credits. And that's the red line here. In terms of actually what's available supply-wise, the actual credits that are being produced today, there's not very many projects that are out there that are delivering on carbon removal today. And so what we're seeing is there's going to be this increasing gap between what is potentially available versus what actually is being demanded. And that, I think, is in some ways is a good thing because it will drive the price up for producers, which is great because we can improve our revenue per credit. But at the same time, we don't want that to go sky high because that could then mess with the actual credit market itself and cause a few challenges, bring in some bad actors. And so what we're really focusing on with biochar and what the work that we're doing at Restored is increasing the awareness for carbon removal, encouraging others to get involved. Doesn't have to just be with biochar, but with other carbon removal projects. And so that's something that we're seeing in the market. Biochar price has gone up and up and up in the last 5 years for a credit itself. And this will continue to be seen, I think. But yes, it's not just a carbon credit. We see its physical properties, as Paul sort of mentioned, and as Alistair has shown in some of his graphs from his trials. But actually, biochar can also be used in applications outside of agriculture. So we're actually looking at applications in things like asphalt and cement production, for example, as a way to decarbonize those heavy emitting industries and potentially be added in as a filler. So our journey so far, we've had a bit of an interesting journey to date. So we started our biochar journey about 1.5 years ago. And since then, we've done a fair amount of work. We actually decided to launch with a podcast. So we found that when researching biochar, at least 1.5 years ago, there was very little information online about how to actually set up a biochar business. There was lots of research on biochar and how good it could be, but there was no evidence or documentation on like, this is the step-by-step guide that you need to go through to launch a project. And so we decided to document the journey that we've gone through a podcast, which is called Grounded. That's won a few awards, actually. So people tend to like that story. And that's been great. But that was really the start of our journey. So it was just sort of like, taking a punt and recording our every waking moment. We then, in order to actually finance the scheme and this pilot project, which we've launched here in Cornwall, we needed to get money. So the way that we went about doing that was we actually pre-sold credits. So we found a company in the name of Bennett Associates. They're an architectural firm in London. They've got an ambitious net zero target and they're buying carbon removal. And they were happy enough to take a punt on us and essentially pre-purchase credits from our project. That gave us some really critical financing that we needed to then put into, to show to others that we'd had some financing and then attract more. So off the back of those sales, we then won some grants. So we got a leveling up grant from Shared Prosperity Fund. We also did a crowdfunding campaign here, managed to raise about £30,000, and pooling all that money together enabled us to buy our first machine and set up our pilot facility on farm here in Cornwall in around August last year. We then partnered with some biomass partners. So as Alistair mentioned, you can make biochar out of all sorts of different things. For us, the most valid use case was taking tree surgery residues. So Plymouth Council deal with a lot of trees, and they need to sort of manage the biomass that comes from that. So we provided a solution to them. At the same time, we take some from our farm that's dead, dying, or dangerous, and we've also taken deliveries from the likes of Cormac, who essentially have surgery teams that are operating daily in the area. We launched our pilot. We started doing biochar applications later or sort of earlier this year, and we're looking now to actually grow our operations. So there's a few snaps of the pilot facility. We had BBC's Panorama down a little while ago, and that's the machine that arrived. This is a CapChar system. Adam may be here in the room, maybe he isn't. So we bought a CapChar machine. That's like the first CapChar system that I think is got set up. So we were sort of a bit of a sort of MVP customer for them as well. And yeah, we've been working on a few partnerships and trials since then. So we've done some field trials on pastureland. We've put biochar down in cattle bedding. We've also done recently a trial where we're doing different concentrations of biochar mixed with fertilizer onto a fast-growing crop. This is going to be a lettuce crop, so we'll see how that goes. And in terms of, I guess, working with the University of Plymouth, it's actually been a massive help working with you guys. I don't think we'd be where we are today without the support. We've had people like Oluwaseun, who's done an internship off the back of the scheme, who's in the room here. We've also had a guy called Ewan who's doing a dissertation with us. And we've also contributed to that piece of work which the University of Plymouth did for CoreServe around offsets and biochar. So what have we learned from the process of producing biochar day in, day out? What I will say actually is also it's very nice to see a bunch of actual producers here. Normally at a biochar or a carbon removal conference, it's people talking about marketplace dynamics and registries and certification, and very rarely do you get people that are like in the weeds of things. So it's cool that there's a panel of so many people that have actually produced biochar, got their hands dirty. But the learnings that we've taken away from setting this up as a business is that sourcing biomass and the right type of biomass is really key. We need a steady supply, and we need to be confident that it's going to be a relatively homogeneous feedstock type. And so that is a big challenge. There is definitely demand for the physical char. We have lots of interest from local businesses that want to use it, whether it's in a tree planting scheme or in one of their sort of agricultural applications. But this market is very immature. I mean, it's not a market. This doesn't really exist as a market yet. It's very much sort of hand to mouth, local sort of dealings. It's not a commodity like you would consider cement or asphalt to be. Potentially that will be the future. But the EU is definitely more advanced in that because it's been around for a bit longer. There is strong demand for the UK credits. And finally, there are policy challenges that we face. I'm being told to wrap up, so I'll finish here. But yeah, from being an operator, we've identified there are a few key policy issues which we're trying to overcome, whether it's environmental permitting or wherever else. But yeah, we've got exciting plans. We're working quite closely with CoreServe and Cormac to identify potential expansion opportunities. So stay tuned, and I'll leave that up.
Yeah. So thank you very much for Alistair and Tom there for kicking off the and a really kind of nice lead in really to the next section where we're going to be talking about soil health in particular. I'm going to invite Professor Mark Fitzsimmons up in a moment just to kick us off, and then that'll be followed by Carolyn Dare from Trim Plants.
Okay, hello everyone. Oops, squeeze in here. Right. Okay. So thanks to speakers before to introduce the topic, and I'm not going to give a gentle introduction, but I'm going straight into the data. So I hope that's okay. We can spend a bit of time talking about that. So this title is that's the one I put in when I was preparing the talk. Perhaps there's a bit more nuance, but there's definitely some evidence of the benefits of biochar in terms of nutrient retention in soils. Now, I've mentioned manufactured soils. Actually, those are the only soils I've worked with. I'm a marine chemist by trade, and happened to come into this field, as it were, through a partnership with the Eden Project, who had created a whole ecosystem with using manufactured soils. And given the commercial pressures, etc., and timetables, hadn't really had the chance to assess how that soil was performing. And an EU programme, European Social Fund, gave us the opportunity to do that in 2010. So basically, if you're not aware of the project and its scale, there are 3 biomes classified. The largest one is the outdoor biome, which is basically a garden, I guess. And the Eden Project has the coverage is almost 8 hectares, and approximately 100,000 tonnes, or almost 100,000 tonnes of soils this manufactured soil has been deployed since 2001. So it's a very significant operation. Yes, and the soil itself has a particular composition based on the availability of material. So you can see from the top 2, comprising 65% of the soil, that it's a highly organic soil, comprised with the green waste and more residual composted bark, also waste sand and lignite clay, which is a waste product from clay operations. And that, using the parameters that one can, that was classified as a sandy loam soil. And being a trace scientist working in the lab, etc., this was a bit of a culture shock to shove everything into a mixer and make a soil and pat it out and make sure that you're not getting any bald clay, etc. But that's the way the soil is made. So that's what we adhere to, and we made the soil. It doesn't have horizons. It's a homogeneous product with some the light brown bit at the end in these soil columns that we prepared were for drainage. That was the waste sand product. But so we created the soil into columns that were enclosed, and those little circles at the top were my ingenious PhD student's idea to try to spread the water and avoid channels. So they're marbles. And so that was a series of soil columns that we set up under controlled temperature to look at the performance of the soil over a 12-month period. So these soil columns are irrigated every day using the Eden Project's irrigation regime. We collected the soil leachate, so the water from the soil that was tapped off at certain periods of different regularity depending on the data that we were getting. And half of the columns underwent fertilization using the product that the Eden Project had used, and that was on 2 occasions. That's the background before we go into the data. So what I think I'd like to concentrate on for this is the top column, which is nitrate. Everyone will have heard of it. A very mobile form of nitrogen that does create a water quality problem because it's not retained by soil, and it's quickly washed into waterways through runoff. And it's also the form of nitrogen that bacteria can oxidize in the soil. So it is, for example, ammonia, which can attach to the soil, is very quickly converted to nitrate. So these black lines that are going down through the graph are the fertilization dates. The higher, you can see S2, the fertilized soil columns, they immediately showed a spike in nitrate concentration when the fertilizer had been applied. And that's not surprising because typically we over-fertilize and add too much nitrogen to the soil, and the soil has an efficient way of getting rid of that, which isn't particularly helpful in terms of water quality, but that's the way it operates. And the second one, which is more unexpected, was the unfertilized soil, which is the orange circles. And we noticed that there was an increase in nitrate at the same time. roughly the same time, and that the concentrations in this unfertilized soil for nitrate were approaching those of the columns where the fertilizer had been added. And not being a soil scientist, I had to scratch my head a lot about this, and eventually came up with a solution based on some literature that I read, that actually the fertilized soil was suffering from had undergone nitrogen saturation, where the nitrogen was being removed, the excess nitrogen was being removed efficiently, whereas the unfertilized soil was undergoing carbon limitation, meaning that there wasn't enough carbon for the microbiome community to access in the particular form that was needed, and therefore it was choosing to use organic molecules that contain both carbon and nitrogen, taking the carbon and rejecting the nitrogen, which is quickly converted to nitrate and then released. So that appeared to be an issue in terms of the way that soil was behaving. So kind of flying through that data, and I'm not going to give another definition of biochar, but the next stage of that project was to look at the potential effect of biochar in addressing those nutrient retention problems with the soil. And that was a biochar that was made through the standard process, containing a feedstock that was available on site. And the experiment ran over a shorter time period, but basically similar soils were packed into pots, and we collected composite leachates from several pots under different conditions to allow us to try to look at the effect of the biochar additions. And we made 3 biochar additions. There are no standardized additions, but there was basically the control 0, and then 2, 5 and 10%, and a weight by weight application. Now, to look at this again, I'll focus just for for purposes of this on the nitrate, but we can see that as the application of biochar increased, the number of the amount of nitrogen retained by the soil was improving, and this green shaded area also indicates that we have some increased microbial activity associated with that. So I won't move on. This is the Fab Soil project, which was the follow-on from Kate's PhD, and that was in collaboration with some businesses. And we also wanted to look at the effect of biochar for soil resilience. So not just looking at what we have today, but to look at flood and drought conditions, which we are predicted to experience and are currently experiencing. So we had soils that were exposed to flood and drought conditions, but also with applications of biochar. An interesting one here outside the flood and drought experiments was that we found suppression of an enzyme that's known to act on lignin, which is a more residual form of carbon, for example, found in wood. So that would potentially delay the need, the fact that a soil would go into carbon limitation if that enzyme can be suppressed. In terms of the flood drought effect, we did find that the addition of biochar improved the carbon and nitrogen percentage in the soil. In terms of its resilience to flood and drought, it was less clear. However, it may be that the biochar addition reduces the extent of carbon and nitrogen loss. We need to do more. We need to do more work on that. So, in conclusion, we have evidence of a positive effect on biochar application, but we really want to look at the future proofing of soils, the manufactured soils that we're working on, but that also applies to natural soils, to see whether that will actually be something that we need to build into future soil management. Thank you to collaborators and also to Dr. Kate Schofield and Dr. Jenny Rhymes, who did all the work.
Hi there, so I'm Carolyn, coming from the Blackdown Hills Eco Hub and Trim Plants. So Trim Plants is a nursery, it's a wholesale nursery. And the reason why I got into this was because for me, land is just under so much pressure. So pollution, slash and burn, climate change, we're always looking up and around us, but we're very rarely looking down. And you've got about 10 billion species in our soils that nobody's really taking much care of. So that's one of the reasons that I got into this. The Trim Plants is a nursery, wholesale nursery. About 5 years ago, we started working with Biochar because they were getting a lot of green composts, which were not providing very good root structures. So they had removed peat about 10 years ago, and they were getting little tap roots. So although the plant looked really healthy on top, the root system was really awful. And we were working with Tom just before this because we supplied some of the plants for the first green wall here. So those plants came from Trim Plants. We also looked around the Blackdown Hills. We're based on the Blackdown Hills. We've got a lot of farmers, dairy farmers around us. And we noticed a lot of people were cutting their hedges, a lot of farmers cutting their hedges, putting it in the middle of the field and setting fire to it. So we thought, well, there's got to be a better way of doing this. We were lucky to meet Rob from Exeter Charcoal, who gave us the first prototype Exeter retort that was stuck in a field, nobody using it. So we had that and started our biochar journey, basically. And since then, we got involved in the Green Wall project with Tom. So our biochar is also in the Green Wall. Adding the biochar actually increased the thermal capacity, but you'll talk more about that in a minute. So I won't talk too much about that. In 22 and 23, we did a series of trials just on our own with multiple pots of lots of different vegetables. So we did 10% biochar, 20% biochar, 10%, 30% in the pots, biochar just at the root, so just a handful of biochar at the root, and compost sample as well. And you can see the lettuce, it was about 3 or 4 times the size, the one on the right, to the 30%, that's 10%. So 30% was actually less growth. The just at the root was less growth. So whether that's got to do with some of the aeration, I'm not sure. And the control compost only was the small as well. So for us, 10% has proved to be really good for all the vegetables that we're growing. In the Eco Hub, you can also see the top picture there. The radish at the top is about the size of a golf ball. It was huge. The other one is a normal radish, and quite a big radish at that. And I thought it was going to be really woody, but actually it wasn't. It was really moist and succulent. So that was our first kind of little trials. So for us, we've been advising 10% for growers who come and buy biochar from us and come to our workshops. I think you've been using 20% in the green thermal wall, sometimes 30%. We've got a test thermal wall as well at the nursery where we've put 20%. 30% potentially maybe for slower growing plants. This hasn't been exactly the same for the plants across the nursery. So I think different plants need different things, but we've not done too much more research on that, on the actual specific plants. We managed to get some money in 2022, 2023 from East Devon Council for an Innovation Resilience Fund, which allowed us to buy our Dartmoor Dragons. So the extra retort is really unwieldy, especially if you're me, you've got to be really strong to be handling that. So we bought the Dartmoor Dragons and we started running a lot of workshops to get people to help us. We're a community group, so we're not a business. We've got the nursery as a business, but I've set up the Eco Hub as a community group. We did quite a lot of work with the Resilience Fund. So we put biochar across the whole nursery with different plants, not in every plant, because we did 1 tray out of 8, just to see if there's better resilience of plants, better growth, more moisture retained. And that was the case in a lot of them. Some of them are very slow growing. The nursery is at the first stage of growth. So often they're sold, so you don't really see what the long term is. But anyway, we sequestered quite a lot of CO2 during that whole experience. And we also started working with Matt from Western Geobuild, who's using our biochar in various flood defence planting type of schemes as well. Then we went on and started a number of trials in our Eco Hub garden, which again is with volunteers, and we donate all of our food to community food larders across the whole area. So that was in 2023 when we set up. And then we had the project with, I think it was GIS, Growing in Small Spaces again with Tom, where we took, I think it was about 400 plants we planted one afternoon in hot sun with different amounts of biochar. And Tom will probably speak about that a little bit more, but we had some fantastic support from the Electron Microscopy Centre. So could actually start looking at what was in these little 9-centimetre pots. And it was amazing to see the hyphae networks just within 4, 5, 6 weeks. They were already setting up, and this was plastic, so they weren't in the ground, they weren't in the soil. They were just in these pots. We do use a compost tea. We've been trialing lots of different fermentations and compost teas. So the microbes, and there's also unidentified microbes. There was worm eggs. There was all sorts of stuff in these pots that were not in contact with the soil. So that was quite interesting to see that. We also had some great images showing what is attached to the biochar. So the red is the carbon, yellow is silica, and you've got all sorts of different minerals and nutrients attaching to the biochar. So there's a paper that will come out about that in very soon. So Tom will be publishing that, and Northwell helped with a lot of the research as well. These were some of the great photos. Northwell at some stage had a real big problem trying to get a root without a piece of biochar on it, because the roots just go right into the biochar, and so they attach, and it's really difficult to find something without it. So you have these mass kind of roots forming, which has been really positive for the nursery. This was a trial I did last year. So over 9 months, planted up 21 beds of about 1 metre 20 each, with 2 different mixes. One was biochar made from conifer, the other was biochar made from ash, and a compost control, times 7. So, and then planted things throughout the whole year through 9 months, and just weighed every single week the harvest. So it was a bit of it was a huge undertaking. Slugs ate everything in the beginning, so had to replant. It was a really bad year last year because it was just so wet. But basically, you can see garlic. The garlic there, the one on the right, much smaller cloves. Weight for the whole 7 beds of the compost only was 1.7 kilos, whereas with the conifer, it was actually 2.4. So there was marked difference on all of them. On peas was similar. There's a 60% difference on beans. Everything we planted, actually biochar was better. And I wouldn't say conifer is particularly a good biochar to be using for vegetables. I think the mixed hedgerow would probably perform even better. But we wanted to see what we could do with the waste material, like Christmas trees. And you can also see the roots on the garlic there is really, really thick. So it's thick rooted. Then we started talking to a lot of farmers locally and saying, could we just add it to the herbal leys as well they were planting? So we've done that on the neighbouring field. We've recently got into working with, we want to get farmers really involved in this. So we've created a regenerative farming online programme and have been running a load of workshops where we include biochar in that whole mix with deep-rooted plants. Getting them to use it around their slurry heaps. We've used it in cow field. We've used it in the cow sheds. We've used it in poultry sheds because it will absorb all of the ammonia from the poultry, plus that it's easier to put out on the field if they've already got it mixed into the straw. We had a new project where we've been able to create a new kiln, which we're going to take out to farms. So we're going to do this actually on site. And we're again talking to the National Landscapes about how they can monetize that for farmers. And then I've just done a last project recently looking at water filtration. And so we've had biochar that we've made at 650, 800 degrees, capturing all kinds of nutrients and metals and all sorts from the local river, which has been really interesting. And I've got really into the PFAS because I've been talking to some American wastewater, stormwater experts who've been studying this for like 20 years. And biochar will really absorb a lot of PFAS. These are some of the people we work with. We've got a thing in the Climate Majority Project book. We've been in the Biochar Guide since it was created. And in the Mycelium Network, we now have about 90 people, 90 biochar creators with us. So we're sharing all sorts of stuff. And we run a load of workshops, so people come and help us. And that's me.
Okay, thank you, Mark and Carolyn. That was excellent and really gives us a good idea of some of the applications of biochar, really a wide range of applications in soil health. Next session is on to water filtration and the applications of biochar in water filtration. I'd like to introduce Frank Foley from the Freak Labs. I've worked with Frank and Shelley for some years now, and I'm going to be introducing myself in a moment, but I'm going to kick off first of all with Frank.
Jolly good. Thanks very much, Paul. Hi there. Yeah, my name's Frank Foley, and I'm from Fleet Field Labs, which is our little organisation we've set up on the Fleet estate, not very far from Plymouth. And our overall projects, are centred around biochar and mycofiltration or mycoremediation, using fungi to remove pollution, specifically or particularly in our case, pollution from water. So I'm going to talk about those. We're a community interest company. We were set up about 4 years ago, and I'll talk about how far we've got in those 4 years. So we started out. We were very gratefully given the opportunity, or started out because we were given some space on the Fleet estate by the owner of the Fleet estate. Shelley, my wife, and I, so I'm an engineer. I started out as an engineer. Shelley's an artist. We both passionately wanted to do something positive for the environment, and we were lucky enough to have some time and resources to be able to, put some time into that. We wanted to do something practical for the benefit of the environment, and thankfully, having some space and a little bit of funding from a local charity funder, we've been able to develop over the past 4 years with some great people, particularly from Plymouth University, some great master's students who've been doing research with us over the years that we've been operating. So we are working with biochar and with mycofiltration. Biochar, obviously my main motivation, for me personally, the biggest thing about biochar is capturing carbon from the atmosphere. And we use it in combination with mycofiltration to capture pollution from water. We're working with the landowners, with particularly the Fleet estate, but with other landowners as well, and farmers and communities to try out these different methods, different combinations, different systems, and with the help of Plymouth University master's students to validate those with scientific evidence. Why biochar? Well, I'm probably repeating something that's been mentioned a number of times now, but again, my concern and passion, my biggest reason for focusing on biochar is this mountain of carbon that we have released into the atmosphere. And no amount of net zero is going to get rid of the carbon that's already there. I mean, over generations, it will be slowly absorbed, but we need to do something about it. And all of the focus so far is about hitting net zero and not releasing more emissions. But as with the example of the bathtub, that's only turning off the tap. That's not actually dealing with the huge amount of carbon that's in the atmosphere already. Biochar as a carbon removal method, and I'm sorry to be preaching to people who probably already know all of this, but it stabilizes the carbon in the soil for decades, centuries, we don't even know how long. It supports healthy soils and ecosystems and works alongside afforestation and reforestation. There's been mention about the scalability. It uses a waste product, or it can be systems can use waste product, and particularly on a local scale. And we believe, Fleet Field Lab, one of our passions is about providing methods that people can apply at their own scale. So we're looking particularly at farm scale and farm cluster scale. And one of the reasons that's important is also about availability of the feedstocks and food security, because obviously the benefit in the soil, farmers adding biochar to the soil and increasing their yield means there's less pressure on industrial fertilizers, on artificial fertilizers, which again becomes a virtuous cycle for the environment and for society. Again, we've probably covered pretty thoroughly the biochar making process. It's worth reiterating that it can be made from a huge range of biomass sources, but we have focused on agricultural waste products, agricultural and particularly woodland management waste, so a lot of brash, wood that isn't of suitable quality to use for firewood. I'm not going to talk through all of the process. Like I say, we've already covered that. And the benefits, there are huge potential benefits for biochar. But there's great variability, and there's been in some ways there's been a bit of overhype around biochar. It's been picked up as a technique, as a method in a number of the international kind of high-level reports with huge potential for scalability, huge co-benefits. But there's also a great lack of practical field trials and evidence from field trials. In the UK, there have been a handful of field trials, but there's scant evidence, and it shows there's great variability in the effect from soil to soil, from climate to climate, and from crop to crop. So we're really hoping. So far, we've had a trial of biochar in cattle pasture, but we're hoping to develop a trial in a yield-based crop, probably wheat or barley, where the yield is carefully measured, carefully monitored, so that we can demonstrate what the benefit of the biochar is on yield. This is as far as we got so far. This is our wonderful Exeter retort. Carolyn mentioned the Exeter retort. This is what we use to make our biochar. We have been frantically making it as fast as we can, but we've only got to about 3 tons so far. It's a lot of work. It's very labor intensive. It's heavy work, and it's incredibly dirty work. There's some lovely photos. I'm not going to talk more about our retort. Microfiltration is using fungi to remove pollution from water, and we've been combining biochar with different varieties of fungi to try in local water sources that are suffering from pollution. Again, with students from the university, we've done a number of trials with different types of fungi and against different types of pollution. Particularly when you have a water course on the Fleet estate that suffers from bacterial pollution. So we've been testing our wonderful Pleurotus austriatus at removing bacteria, that's E. coli classically, bacteria, nitrate and phosphate, both in dairy wastewater and in sewage affected water. And briefly showing very interesting results, great variability, particularly with the microfiltration, because you've got no guarantee about what pollution is in the water. It tends to vary greatly with time. But we have demonstrated on a number of occasions, we demonstrated significant reductions in bacterial pollution, phosphate, nitrate, and this one here is actually was quantified for oil and grease, fats and oils from a dairy wastewater plant, from a dairy wastewater, and it showed a significant reduction in fats and greases going into the local river as well. We want to continue doing what we're doing, testing new systems, testing different combinations, and validating with scientific evidence, thanks again to Plymouth University and their students. Finally, one of the big challenges for me making the biochar is crushing it to the right size to use in the soil. I've killed a number of garden shredders by trying to crush biochar. It takes forever, it's hugely dirty, and it kills the machines. So I've designed and am getting fabricated at the moment this biochar crusher to use for exactly that purpose. And that's the end from me. Thanks very much.
Hey, thank you very much, Frank. So Frank and I have been working together for a few years now. I think we've had 6 master's students in total with 3 labs working on water quality, many more working on soils and soil augmentation. So, but what I want to talk about is basically our preliminary results that we've got from the work that we've done on water filtration with fungi, and also thinking in the future for biochar and the work. So the images that I'm putting up attributed to Caleb and Rihanna and also Aaron over the last few years, past master students. So we're aware of the dire situation. I think everybody here is aware of the dire situation in terms of our sewage pollution and river water quality. According to government figures, 2022, 300,000 national spills and incidents. For our water authority, South West Water was one of the worst performing. Nationally, sewage dumped into designated waters over 5,000 times in 2022. Resulting in sickness and failure of water bathing regulations, and diffuse pollution from agriculture, in particular from phosphates and nitrates into our water courses, probably contributing on average about 50% to that additions from water treatment plants. Yeah, so a little bit of a dire situation, so much so that from a biological point of view, only 14% of our UK or English rivers are in a good ecological status, and the main cause of that is phosphorus and nitrogen levels in particular. So that's kind of setting the problem. And this has led to a loss of biodiversity. So this particular image here shows surface algal growth, which causes a blanket over the surface of the water and then dies and sinks, and then you get eutrophication and anoxic conditions. So real problems. Now, in the past, I think the old adage from the engineers was the solution to pollution is dilution, but I think we can all agree that you can only get so much dilution from our river networks, and we've certainly exceeded that. So what can we do? Well, in terms of water filters, biochar water filters in particular have been around for the last 4,000 years or so in Thailand, northern Thailand in particular, used in agricultural systems to improve water quality. So it's something that's again by no means new. But in terms of the kind of nature-based solutions for water treatment, biochar is well up there. And here's a few other favourites of mine. Sphagnum moss, in particular, using moss as the filter material is very good at taking out particulates in particular, and has some adsorption. So biochar in particular is a material which will absorb onto the surface, in particular high ion exchange over that surface area, which is why it's quite good for things like inorganic pollutants, in particular some of the nitrates and phosphates, which will absorb onto it. So it has in terms of the efficiency, it's very customizable. Talk a little bit about what you can add to it in order to make it customizable for your target pollutants. and its longevity is pretty good as well. So if you're using it as a filter, unlike things like the sphagnum, for instance, where you get a loss of efficiency over time, and fungi in particular, because it's a living material. Have a chat a little bit about some of the data on some of the fungi, and mycorrhidiation is it is less effective in the long term and needs replacing. And then we've got our constructed wetlands, which we do quite a lot of work with at the university here on paludiculture, looking at constructed wetlands for treatment of nutrients. So we've already spoke about the kind of scalability of biochar. We've got plenty of feedstocks that we can use to produce biochar, readily available, low in terms of its technical, and it's got many co-benefits as well, such as our carbon sequestration, soil amendment. So we've got potential options here. I should say, mind you, in terms of the actual use of biochar for a water filter, unfortunately that does not count within the carbon credits at the moment. There's still quite a bit of work to do to look at the durability of that when you've used it as a filter. But potentially in the future we could have that a co-benefit of carbon sequestration as well as our as the actual water improvements. So I'm going to start off talking a little bit about microfiltration, so picking up on what Frank has done, because this is what most of our work that we've done with the Fleet Labs have been on. And in particular, fungi very close to my heart, so I started my PhD on fungi. I'm a mycologist, I suppose, by original training, and Frank and Shelley have been using the summer oyster mushroom in particular, Pleurotus, species of Pleurotus, and growing that with wood chip and straw to make a filter material, a filter substrate. So the thing about fungi, which is obviously it's as well as the physical absorption of pollutants, they are living, they're enzymic. So you've got production of extracellular enzymes which are able to decompose organic materials, which we've actually found very strong, powerful results, particularly for things like milk, and which is a real problematic pollutant in our dairy industry and our farming. Fungi in particular, microfiltration, you do have some problems with that, but certainly shows good potential. So this is the Holberton Brook study area where the Fleet Labs works and where our students have been working, and this is a small tributary that runs down into the River and on that tributary there is a sewage treatment, a wastewater treatment owned by Southwest Water, which sits in the middle of that kind of catchment. And we've got the opportunity to look at filtering of the contribution that comes from that wastewater treatment. So we've got areas that we can sample above in the catchment and below. And this is also a highly intensive agricultural area as well. So we've got agricultural material that's been washed down into the river. So as Frank said, basically, what we can do in terms of field trials to test out the suitability of these fungi in situ in the field is to put what is effectively what's called a burlap, these bags which contain the myceliated wood chip and also the straw growing out there, and then put them in a series of blocks down the river channel and look at filtering above and below both the sewage centre, and also look at just the substrate on its own. So this is these are the burlaps along that river, along that small tributary. At the top there, we've just got unmyceliated substrate. Then we've got myceliated substrate, and then in this particular one, we've added iron as well. And iron is known to be particularly good for scavenging phosphate, at least in its reduced form. So this is just some of the results from Rhianna Trim's data showing the water, the control, so what the water is, and comparing to the control in terms of these parameters that we've tested for, which are nitrates, colony forming units, phosphates. And this basically shows the data for the physical barrier, so the unmyceliated substrate with the fungi, with the microremediation and microremediation with iron. And we've had particularly good successes, very high significance with the coliforms, fecal coliforms and total coliforms, and also significant effects with the nitrates. The iron itself wasn't so successful. I think the iron we used wasn't in the form that we needed in terms of the reduced state, but certainly options there going forward. We've also, just to kind of finish off on, what we're really looking at doing is combining our myceliated substrate with biochar. And these are just a few scanning electron microscopic images, basically showing the hyphal network, which is able to grow through this porous substrate and increase the areas for absorption within that. So it's really kind of powerful. You've got the physical nature of the biochar, but you've also got the biological nature of the mycelium. So what we're looking basically at doing is combining these biochar and the myceliated substrate to produce some tests, and we need to do these in the laboratory using much more controlled conditions, because the problem is in the river, very dynamic in terms of the pollution environment and the flow environment, very difficult to pull out significant results. So that's the next step, and we hope to go on and do that maybe with a PhD student in the over the next few years. So thank you very much. Okay, while I'm up here, I'll introduce the next. So we're moving on now from water onto using biochar as an insulation material in building and construction. And I'd like to introduce, first of all, Jack, coming up, Jack Moorcroft from the university, to come and talk to you about that. Thanks, Jack.
Thank you very much. So yeah, thank you very much for the warm welcome, and it's great to be able to shift the focus onto buildings. And what a better environment to be in. We have 3 living walls here, the internal one behind us and 2 there. And what I really want to do today is just reflect on our experiences over actually a 6-year period of monitoring and investigating living wall systems, research that began in this very building. So living wall systems, what do we know and what don't we know? So I'm going to cover living wall systems in a nutshell. I'll set out the benefits of living wall systems and then the performance evaluation. And that really sets up the work that Tom's been doing and Natalie of adding biochar to living wall systems. So a few local examples. Well, I've already mentioned the Sustainability Hub, where we have these modular phytotextile pockets, and that was installed in 2019 and monitored since its installation. We have the Genesis building in Plymouth. So we weren't the first in Plymouth, but there was actually the Genesis building, a continuous hydroponic system that's down on Union Street. We have Exeter Science Centre, and Natalie in a short while is going to be reflecting on the experience of installing a living wall system there. And a few more in the pipeline. And if you look beyond the southwest, you can see all of the work that's being done in places like Manchester and London, and the growing interest in living wall systems. So a great time to be doing this research. Why are living wall systems so important? Well, it's about the harms that are associated with buildings. The built environment is associated with 34% of energy demand and 37% of carbon emissions globally. But there are also a range of biodiversity harms associated with buildings that the climate crisis is intertwined with. And living wall systems are part of this important family of nature-based solutions. And what characterises a nature-based solution is 2 things, really. That they are supported and inspired by nature, and also that they provide a range of co-benefits too. So, living wall systems in a nutshell. Well, when we think about greening a facade, there are 2 ways that we typically do this. There's the low-tech way. There's a green wall, which is simply the greening of a vertical surface of a building with a selection of plant species. And, that can be something really quite low-tech, like, hanging plants or climbers. But a living wall system is much more involved, because it involves installing a planting substrate actually along the wall into which the plants root and grow. So it's characterized by the planting substrate along a vertical surface and the plants root and grow into that. There are lots of types of living wall systems. And as I mentioned at the beginning, much of our work is actually focused here on these modular systems, the modular trays, the geotextile felt pockets, but other living wall systems are available. And in terms of the benefits of living wall systems, over the last year, we've sort of really reviewed these in detail as part of the Entrepreneurial Futures project and conducted a literature review. And we've also measured some of these benefits ourselves, so we have the data to back them up through the monitoring we've completed. They range from all things, reducing heat losses, and also the cooling effect from evapotranspiration from the plants. And that's associated with reductions in carbon emissions. We've also found from literature lots of other benefits, such as managing rainwater, treating rainwater. There is some evidence that having a living wall system improves the health of occupants. They change soundscapes, noise reduction and noise absorption, air purification, reducing volatile organic compounds and particulate matter, and of course, simple things. Some people believe they improve buildings' appearance. And as an environmental building group, what we've been doing through our research is actually getting the data, doing the hard data and measuring the performance of them. We've been doing that in a few different ways. And as I said at the beginning, all of this really started with the Sustainability Hub, where we had these living wall systems which were retrofitted to masonry walls in 2019. We also looked at the long-term benefits of that living wall system as it's been replanted, and also as biochar has been added to the soil, and also the impact of irrigation system. And really 5 years ago, what we did was we conducted comparative monitoring, an in-situ U-value measurement using a heat flux plate and indoor and outdoor environmental monitoring. And we did this comparatively. So we compared parts of the wall there that didn't have living wall system with parts of the wall where living wall system had been applied, and we found that the heat losses were reduced by around a third, and that work was published in 2022. We've also gone into the laboratory and actually focused on the planting substrate. So we've investigated the different properties of that planting substrate and what could actually be installed along the wall. So looking at the thermal, moisture and physical properties, and that's included some examples: green waste compost, fab soil, which we mentioned earlier, but more recently biochar enhanced substrates. And one paper has already been published and one's currently under review. We also have some more experimental work. So we've looked at testing rigs, and they sort of currently sit at our labs in 20 Ensley Place that we think could help installers to actually test living wall systems without actually pushing them onto the wall, and sort of looking where that piece of work goes. But it's lots of these performance evaluation techniques that the university is able to facilitate. The physical measurement, the monitoring, the moisture monitoring, also, things like thermal cameras that we've studied living wall systems with, and also potentially sort of modelling and simulation, and also looking at the whole life carbon associated with living wall systems. And as I say, all of that backed up by a literature review. So what I'd like to do now is to hand over to Tom, who'll talk a little bit more about biochar.
Hey. Thank you, Jack. So thank you, Jack. So as an introduction, Dr. Tom Murphy. There's lots of Toms in the room, I'm sure. I'm the Tom who works with Carolyn previously around biochar and testing. I'm an academic at the University of Plymouth. So today, very briefly, I'm going to talk about how we use biochar in the context that Jack's just outlined, so within a built environment context. So in terms of, and this is quite a nice opportunity to link quite a few projects here, actually. So obviously, we thought, okay, well, let's, following on from that result of, okay, we know living walls are potentially
saving us a lot of energy and have lots of potential as a nature-based solution. We did some testing looking at that substrate. So I'm just going to show you a little bit of data from the study that Jack mentioned, which is now published in Soil Use and Management. And as part of that study, we basically tested the role of 3 different substrate types and looked at in a laboratory how those soils and their thermal performance was relating to the moisture that they contained. So it's probably a bit small for those of you at the back, but as a brief summary, we have 3 mediums. So one is a fab soil, so the soil that Professor Mark Fitzsimons introduced previously with his testing, which is deployed at the Eden project. We tested a green waste compost topsoil mix, which is widely used by the building trade and landscapers. And then we looked at testing this biochar coconut coir mix, thinking, okay, well, maybe that's perhaps a more sustainable option. And one of the striking things was the big difference in how they were performing thermally. So we see, I'll read it out, but we have big differences in the thermal conductivity between the green waste, the 3 different mixes, with our biochar coconut coir mix really maintaining right from a spectrum of very, very dry all the way to very, very wet, a very low thermal conductivity. So in terms of those benefits, it's really maximizing that potential in its application potentially in a living wall setting. So that made us think, okay, well, what is the role of biochar? I'd never heard of biochar actually at this point. It was something that was fairly new to me. So again, this is a project. So leading on to that, okay, well, what is it about biochar in particular that lends itself and might explain some of these benefits that we were seeing? So was it biochar? Was it the coconut coir? But let's have a look at biochar. And one of the things we did is, Carolyn mentioned as part of Growing in Small Spaces project, we used the scanning electron microscope center that we have in Plymouth to essentially assess the structure. I mean, I think that's one of the things we think about insulation. We think of that high complexity. This is what biochar gives us. It's highly heterogeneous structure, lots of a porous space of different sizes. So that works for the biology and for filtration, but can it work also for a thermal performance? So Jack introduced so this is sort of hot off the presses, actually in review in the Journal of Biochar. And it's we did some testing, essentially looking at 3 different treatments again, so really digging down to the biochar effect. So we tested a green waste compost, 100%. We compared that with a 15% biochar mix and a 30% biochar mix. And we did, again, a saturation test looking at thermal conductivity and soil moisture. And a big thanks to Joshua Batum, who was an MSc student, actually a BSc student at the University of Plymouth, and led some of this trial. And again, the biochar that we used for this was kindly gifted by Trim Plants, so thank you, Carolyn and Terry. But one of the key standout things we found is that with those different mixes, we saw, firstly, particularly at those lower soil moisture levels, so between 20 and 40%, we see a much lower thermal conductivity. And that we see essentially a halving of thermal conductivity by adding that biochar. So essentially, we're finding that an addition of 30% biochar was almost halving the thermal conductivity potential of that soil medium. So I think that's really, really interesting findings, and we found this was a non-linear approach. So I've been told to wrap up, so I will. But I think it's just maybe as we go into the discussion section, thinking about how and where we get our biochar from, but also we talked about the context and the specificity of the type of biochar we get, can we start to think about using different types of biochar for different purposes? And one of the things that the futures will be thinking about, how can we use this particularly in terms of a thermal performance context, which is the best medium to use. So thank you for listening.
Dave, thanks, Jack and Tom. Moving on to our last session of the day before we go into our Q&A session. This one's going to be online, so we're going to be joined by Natalie Whitehead from the Exeter Science Centre. Hi, Natalie. Can you hear us okay?
I can indeed. I hope you can hear me all right.
We can hear you very loud and clear. So welcome to the Sustainability Hub to you, and I will hand over.
Thank you so much. So let me share my screen. I hope that's coming through all right. So hi, everyone. I'm sorry I can't join you in person. We're super, super busy at the moment, but it's a real delight to be able to join remotely. I've really enjoyed the talk so far. And this talk follows on. It's going to be brief. It's really just following on from what Jack and Tom have been talking about living walls for net zero. We have been using this wonderful biochar mix from trim plants, and many of the plants that we have in our living wall that you can see on the left here, it is from trim plants. So we're really excited about that. And we just want to give you an insight into our kind of live research project that we're working on with the University of Plymouth researchers. So my role, really, I'm one of the co-founders and co-directors of Exeter Science Centre. We're a small charity, but with big ambitions to make a network of science discovery centres around the Southwest. We work on projects, events, exhibitions, research as well, supporting research to connect the public with global issues. And so we're very, very passionate about, tackling climate change, making people aware of the need to do so, and finding tangible ways to do this, and meaningful ways, and creating a living wall and using that as a live research project is a really exciting opportunity for us. So we were really, really delighted to work with the University of Plymouth research team. We received funding for their time to contribute to this project, which we're really grateful for, from the sustainability funding. The Net Zero Exchange funding as well has supported our internship. Amy Thomas joined us for about half a year part-time to support the public engagement with this project. And of course, we have trim plants as well that we've been using their amazing biochar. And there's a big wider project here as well, including the client. So we don't have a physical building ourselves, but we're really lucky to have some office space above an amazing cafe, and they were really keen to create a living wall on their building, and we of course were grateful to turn that into a research project. So that's why Lumi and Mello are listed there as well. They're the clients. So let me give you just a really quick summary of this research project. There's Tom and Jack there in front of the living wall setting it up. So the focus of this project was to understand how effectively the living wall would shield the building from the sun in summer. You've heard already how living walls are really great for providing insulation value. Of course, you need insulation in hot summers, and this is only going to get worse with climate change. In particular, this building is south-facing, get a lot of sun in summer. This was a thermal camera image before we had the living wall installed. On a reasonably warm day, 27 degrees outside, you can see the temperatures at different points there. So the paving is about 48 degrees and the wall is about 40 degrees or so too. So really, really hot in terms of radiant heat. You'll notice there are some plants there already. There's a little tree in the left-hand side, plants are cool, and we wanted to demonstrate that with this project. So this is what the building looked like beforehand. You can see it's a kind of metal-clad building with very little vegetation going on, and in particular, we wanted to use this not only as a project to improve the thermal performance of the building in summer, but also to increase biodiversity on the site. We are based on an industrial estate, right where that little pin is showing there. Next door, we have this kind of and over the railway line, we have a beautiful kind of nature reserve, but really this area is very grey, very concretey and tarmacy, and we were very keen to use this as a demonstrator for how buildings on industrial estates can be greened and therefore be better for biodiversity and have lots of other benefits too. Let me just give you a very quick overview of the results. We've only really had the living wall installed since last November or so the plants have been settling in. The research team, as you can see here, have installed the sensors, and the sensors are those little kind of white pale boxes that you can see on the living wall. We're testing 3 different plant types at the moment. We're hoping to extend that with future funding to more areas on the living wall, but those top 3 different plant types are being studied. We're trying to understand how different plant types, how different forms and habits have an effect too, and these ones are 3 very, very different ones. So the results now, they're not quite as scientific as I would like, because we actually haven't had all that much data, nor the time to analyse them fully. So it's really just a bit of an insight. This is the picture of the finished living wall compared to the original one. It's a big difference. And this is the thermal camera image to show you just very loosely how much of a difference the plants are making. This was taken this Monday, so it was quite warm weather. I think it was about 20 odd degrees outside. As you can tell, still though, despite it being not absolutely baking hot, the building where the living wall is not there's no living wall at the top part of the building, is about 36 degrees on the surface of the wall, and yet the plants are producing a noticeable cooling effect, particularly those ones where the plants have actually filled the space around their pockets. There's a zoom in to the right hand side of that, and you can see that some of the plants, these ones in particular, are the Carex, that's the bottom right, and the one in the middle is Jacobia maritima, if I pronounce that correctly. They're doing really well, so 21, 22 degrees compared to maybe 40 degrees on the surface. So these are just very, very much preliminary results to give you an idea of the cooling effect. We're hoping to get some more accurate data along very soon. So do stay tuned. This was really just a bit of a way to highlight that practical application of biochar in the living wall system that we have, and also just this really exciting research project that we're really delighted to be working with Thomas and the team on. I've got a few asks for you here, because we really would love for you to stay in touch with the project, fill in the survey if you have time to let us know how you feel about the living wall, but crucially as well, a bit of a plug for you to work with us if you're interested in studying the biochar effects on our building, or looking into any of the other things that I've kind of mentioned there in terms of, and you've seen today about the benefits for living walls, about pollution, biodiversity and things. If you want to study that with us, get in touch. We've got a wall designed to be studied, so we'd love to work with more of you. That's quite enough from me, so thank you so much for having me.
Thank you, Natalie. I believe you're going to be staying with us now, because we're going into the question and answer session. So what I'm going to do is invite all of the speakers to come and sit in a row at the front here. And Saul, who's over at the back there. Hi, Saul. Saul's got a roving mic, and if you could basically just say who you are and who your question is addressed to, then Saul will come around and pass the mic to you for questions.
That's right.
Give him that.
Yeah. Oh, okay.
So you don't need a mic to just talk.
Okay, that's all right. Is that okay? Just talking. First, apologies. When I was 16, I asked my chemistry master what happens to carbon dioxide. And he said, don't worry, it gets puffed in the ocean. Well, it was 1957, and I apologize for not being persistent. And I think one of the great things is to get it proper right. You have to be asked questions. 2 questions. You're going to put this stuff in the soil. How much soil before you've saturated the soil, like we're saturating the oceans? And as a civil engineer and a building owner, I'm interested in the certain properties, but would I do just as well the handbags of the vermiculite, or anything but polystyrene we're being forced to use at the moment? But I think that's wonderful. I'll come back if you've got other questions. That's quite a broad questions. Anybody want to pick up on that?
So basically, we're looking at the potential, yeah, to store CO2.
No, it's fine. I can do it. That is all actually. But where we were in 1957. Yeah.
At the moment, there's legal restrictions on what you can put. So it's 110 tonne per hectare. So we're kind of restricted from farmland at least. But that biochar will start to go down and down and down and down and down because the worms, dung beetles, everything will actually take it down. And I was on a call with geologists last year or the year before, and 2 huge studies came out, and they reckon that biochar will stay in the soil for 500,000 years. So it'll just come back up as sedimentary rock. So it may not be a problem. It will start to just go into the core, towards the core or whatever. So it'll just go down.
Thank you.
Like, show you what walls like.
Yeah, so I just pick up on the vermiculite point, because I think that's an important one, and maybe it highlights. So I suppose the difference with vermiculite is obviously the carbon intensity. So I suppose that would be my response in terms of biochar being a fairly good option. You know, that the intensity.
I want to see the comparison of benefits, how good yours is compared to the plants. Okay, because as a building owner, I'm just interested in with this pressure to reduce my demand for heating.
Yeah. So I don't think I haven't compared it directly with vermiculite. I suppose what you'd think is hopefully there'd be the co-benefits. You know, I guess that's one of the things, isn't it, with biochar?
You know, as a landlord, I would like to go and buy a carbon sequestration and stop.
Yeah.
Crucifying the building until we can sort out the right thing to do.
Yeah.
I would like to, but I don't have a government that thinks broadly. Richard, I'll shut up.
Questions? I see a hand up over there. Would you like to shout out your question?
Right. I mean, this is for Caroline, I think. Thinking about the plants that you were going with and stuff, you mentioned about trees. Actually, have you actually done any trials with trees as well?
Tom has been doing trials with trees. Not quite yet. No, we are going to. We've done it with plants across the nursery. I think there's a really nice study that was done in Stockholm, maybe 10, 12 years ago, where it was actually a stormwater kind of trial. They were trying to collect the stormwater, and they've built these massive bunkers, concrete bunkers, filled them with biochar, tiny bit of gravel. They're about 2 meters deep, filled them with a little bit of gravel at the bottom, and they planted the trees in there. And what happened was the trees grew 30% more, but the actual health of the tree was really, really much improved. They weren't pushing up pavements anymore. And then we're also working with Steve from YGS Associate Tree, and they've been planting microforests in schools. And he's using a Japanese method, but using biochar in that. And I think 2 or 3 years ago, when we had that really hot summer, he had microforests that he planted without biochar, and they completely died. Those trees died, but the ones where he'd used biochar survived and actually thrived. So there is something about, I've seen some evidence around the kind of shock that whips get if you're using biochar. It's a lot less. And it seems to be there's a better survival rate. So whether that's the moisture, whether that's the aeration, there's a very nice study as well with ash dieback that Reading University have done. And trees that were treated with biochar once a year for 10 years haven't succumbed to the same amount of disease as those that weren't. So there's a few projects around.
Answer that. Thank you. Questions?
I have no idea about biochar when I come to this session. So I said this is like an intensive master class straight away. My question is, biochar is not biochar means different thing, depends on what you put in to make the biochar. And so different material will generate different type of biochar. So impact will be different in terms to your plant, in terms to the tree and the water. Am I correct? Because So do you have any research? So for instance, I'm interested in the food waste and how the food waste will contribute to make the biochar and then return to use in the soil for the rice plantation or the mangrove in the coastal area. So I wonder whether different type of any research about different type of biochar and the different level of impact. Whether you have such research, you can refer me to. Anybody can. Sorry, I'm just listening to what you have said. I feel that different. You seem to talk about biochar is the same thing, but biochar means totally different things. Come from different background. I come from rural area. Biochar tend to made from I would say rice, the harvest waste, and they will have a different impact compared from the industry waste,
Yeah, there are a lot of studies actually done on different feedstocks. There are many studies, mostly in the US that I've found so far. We've done a little bit with 6 or 8 types of different woods, so dogwood and rhododendron. I mean, I would never use laurel, for instance, in our vegetables because we don't know at what degree the arsenic disappears from it. We just need more research, really, because we don't know, laurel is sort of arsenic, so you don't really want to plant that in your food. It might be very good for trees because some trees, like arsenic, they grow better with it.
So can I just ask the producer then? I think it's Tom. So when you choose to produce biochar, do you tell the consumer, say, this biochar is made by these 3 ingredients?
Yes. Yeah, we have a relatively transparent approach to sourcing the biomass that we take. I mean, ours is whole tree biomass, so it could be twigs, branches, bigger parts of the tree, but we get them from, like I said, different tree surgery operations. So we'll know what type of tree it is that we're turning into biochar, and then but we only use whole tree biomass. You could make biochar from manure, as Paul referred to in his talk at the beginning. But yeah, each no 2 pieces of biochar are the same. They have a lot of different properties. Some will do well in other conditions versus others. Some are more challenging to convert into biochar than others, depending on the moisture content as well. Particularly taking a very wet biomass like a manure, you have to dry it, and that's a whole challenge in and of itself. Which is kind of like, some people in biochar say the pyrolysis is the easy part. The difficult part is actually processing the feedstock before it goes in. When you're getting to the larger scales.
Yes. Thank you very much.
Just to add to that, it's a meta-analysis that I came across when I was writing a paper a couple of years ago that had investigated the use of biochar for reducing nitrous oxide emissions. And the take-home message was that it seemed to be and there would have been a variety of applications, and certainly at that scale of study, but the conclusions were that around about a year, the benefits were clear in pretty much all of the applications, and after that they became more variable. But some biochar applications in certain environments continued to be efficient in terms of the nitrous oxide reduction.
So for PFAS, there's a really nice study from Rowan University in the US where they've taken cow manure, biochar, and it's something like 95% absorption of PFAS or chemicals. Whereas for other woods, it's less. So yeah, it's different.
Okay, thank you.
Good question. Any more questions from anybody hiding behind me?
Thanks. Really interesting talk from everyone. Thank you very much. Coming to Alistair, you were talking about the financial thing rising as a result of the tree planting ambitions in Council, which sound great. Do you think how are we going to be able to scale up to deal with all of that potential biochar production? Because we had obviously you're in early stages at Restore Tom P, and you've got some mobile units that you're taking around to farmers. That's really interesting thing.
Yeah.
Is it going to be distributed, or are we looking at one big central processing plant? What's the vision?
Yeah, I think maybe it's a mixture. I know Tom's looking to scale up his operation, and maybe that's a sort of a drop-off site for various arborists and landscape workers, which might be on a sort of subscription basis. I know a lot of sort of gardeners struggle with getting rid of their waste at the moment due to sort of like high gate fees. So maybe there's an option, where there's a centralized hub where everyone can pull into it. But something good at the with the sort of conifer plantations, they already have the sort of access roads embedded within their sites, which can which would work well with things like the Exeter Retool, which is some of the kilns that can be attached to the back of vehicles. So I think it can be a multifaceted approach, but also just trying to build that network of landowners who have sort of woodlands on their land and new woodlands that need managing. And trying to sort of make those links.
So a really good question actually in terms of life cycle assessment, because of course you could be, if you're transporting your feedstock around the country, undo the good that you would have in terms of the carbon sequestered. Sorry, was there a
something that as well? Is it, so the question is around like how do we scale biochar production? So a big part of it. So I think there's a few of us here. We all make biochar at a small scale currently, and I think all of us would like to be able to do it at larger scales. The technology exists. You can. I mean, it's expensive currently, but you can build machinery that is producing thousands of tons a year. The world's largest project is in Exomad. And they are producing tens of thousands of tons of biochar a year from a big plantation that they have where they're producing a lot of timber. So that's like on the other end of the scale. But the technology is there. It's just accessing the finance in order to be able to get that. And given biochar is a relatively new, it's been around for thousands of years, but in its current state as a sort of business opportunity, it's pretty new. And so investors, banks, traditional financial mechanisms seem to spray at very high risk. And so it's quite difficult to access that money to actually scale the operation. So that's a big challenge that we're trying to overcome at the moment.
Can I add to that as well? Sorry, I think that there are issues around the risks of industrialization and going to big scale. The energy used to transport materials then becomes an issue, and in other big scale biomass projects, particularly energy production, there have been some serious challenges with sourcing biomass in a sustainable way. So I think there is an appropriate scale. It's probably larger than what we're doing, collectively, but it's not the big. Well, my opinion is it's not the big industrial scale that happens in some other fields.
Thank you. Just going to go, Tim might come back to that, but online questions?
There's a lot of online questions that come in.
There is,
18 or so, but the majority of them come from Andrew Rosen at the University of Exeter. Perhaps we'll send them over to the panel later to get out to that.
Okay.
There's a few that have come in around the kind of one particularly from Catherine Price, and she's asked which carbon trading company is allowing the credit to be claimed at the point of application. And there was also some around, where are they selling the credits now, and where are they kind of expanding that? So
I think that's a question for John.
Yeah.
So it's what platforms are. Sorry, can you just repeat?
So the initial question was kind of the carbon trading company, which carbon trading company is allowing the credits to be claimed at the point of application? And then where are you selling the credits now? What marketplace are you using?
So we've actually got the registry in the room here, Adam McCapture on the back. We've retired our credits under the Capchar's biochar code, UK biochar code, which is one registry of a bunch of others that are out there as well. So in order for us to retire and claim credits, we follow a code like the Capchar one. We will then produce our biochar, we'll do a life cycle assessment, we'll get that third party certified, and then we'll be able to, and we provide that evidence to the registry. and then we'll ultimately be able to retire those credits based on the information that we've provided. So that's when then the buyer gets their certificate. And that's sort of what we've been going through over the last 6 to 9 months, is sort of retiring our first batch, delivering those, which we'll be doing in a couple of weeks, and then continuing on. There are other standards and registries out there. So Isometric, Vera does one that's very extensive, Puro and others. So there is a lot of work involved with certifying and getting sort of your project green mix in that sense. I hope that answers the question.
Yeah, and in terms of where you're selling them now, is it through a marketplace?
No, so we've sold direct to buyers since then. It's all in the voluntary carbon market, so bear in mind that these are all voluntary purchases. There's no government mandating this, and so companies that buy are buying at their own risk. But at least our buyer, Bennett Associates, for those credits that we sold initially, were comfortable with that risk because they felt as though it was a worthwhile sort of project and opportunity for them to get involved with, and also to help the industry. But you can sell via a marketplace, right? And there are others out there like a Supercritical, a Patch, and whatnot, who will try and aggregate for you.
Tim for the last question, I think.
Yeah, thanks very much. Well, there were two actually, Paul. So forgive me for that. There was one about scale, and I think we've kind of covered that quite a lot there. But I need to say, how do we enable scale of UK project deliveries in this country on the basis that you know, I think you put up CDRYI up there, and you mentioned Excellent Green as one of the major providers. And of course, you're a big buyer, which is Microsoft, so they're buying 80% of those CDR credits, and they're cutting those OTC deals, aren't they? And saying, okay, we'll just make that use. So what? And when there are buyers clubs, I mean, you mentioned Isometrics, they support the course set up, but not by originally they're kind of the big buyers clubs. And I wondered if there's a suppliers club that needs to set up, or whether that would be a way to scale sufficiently those kind of individual projects. I don't know if that really exists yet, or whether that could go anywhere. So that's one question. The second question was about core understanding of GCSE biology was that those fungi degrade biochar. So if you're mixing fungi and biochar together, isn't there an opportunity to degrade and therefore damage the durability of biochar if it's then being sold on the market? So you're damaging the durability and raising the delivery risk.
I'm going to come back to that question. But I'm going to go first of all to the initial question, which I assume that we've got the folks in the room here. Collectively, is there an opportunity for a buyer's club?
Well, I think the councils are trying to do it. The Shropshire Council have invested a lot of money into quite a big pyrolyzer. They've now been talking about the Geog councils. They're using it for filling plot holes and all sorts of different things. So they're trying to do it together. In the Mycelium network, I think we're about 80 producers. The issues were all quite small. Carbon Gold has just been sold to to Westland's big compost company. So I think we're going to see changes in that compost market as well. So there's a lot going on, but we would rather, or at least I would rather, I might not speak for the rest of you, but I think it'd be nice to keep it local, produce it local, use it locally. And if we can have a whole network of people, we are connecting with each other since a few years, connected with quite a lot with biochar makers. But I think the risk is, on our course sometimes we have Jackson EDF, and then it's going into a completely different scale. So
my 2 cents on the scaling of UK biochar. Like, if we're talking about scaling UK biochar from a carbon removal standpoint, the UK might well not be the best place to do this. There are other places, geographies that have loads of biomass that's readily available, and it's a waste stream that can be tapped into. So Brazil, for example, is a great sort of place to look. That doesn't stop the UK from being a great place to do the research and development and scale to a certain point. Actually, continue to maximize what waste streams we have that we haven't tapped into yet. And there are actually quite a lot. A lot of people say, there's just not enough biomass. And I think that's actually, from the experience that we've had, that's just not true. There is loads of biomass all over the place, particularly in the UK. You just haven't tapped into it. You haven't been able to get into the supply chains where it is and where it's being managed perhaps poorly. So there's probably going to be biochar, I think, will grow in the UK, but I think it will grow in two ways. One, through a decentralized sort of smaller scale operations being set up locally, similar to what we all are at the moment. You know, we are sort of smaller sort of producers, and that I think will continue to proliferate, hopefully. And then you will get sort of larger scale, more industrial operations that are setting up, which have more of a focus on the carbon removal, I think, aspect to it, and will sell biochar wholesale in sort of various applications, perhaps more of an industrial focus, looking at sort of using it in the built environment. So combining it with, concrete or asphalt, for example, that's what we're looking at.
Thank you. I think I'm going to draw it to a close now. Thank you very much. I'd like to thank all of the speakers for their excellent presentations. So thank you all. Shall we answer for that? To you as the audience for a good set of questions, and the folks at home as well. And to the net zero team at the back, all there for keeping us, Becky in particular, who has done a lot of the organising. Thank you, and to Saul and Sam and Claire and the rest of the team. Thank you very much. I don't think there's any reason that people need to rush off, is there? Nobody's using the room, so please feel free to stay and have a chat and maybe answer some of those questions that we didn't get round to asking. Thank you very much, everyone. Bye now.